Greetings, netizens. Space-time is one of the great mysteries of our universe and consists of a mathematical structure that encompasses all objects and physical phenomena of the cosmos. Since Albert Einstein formulated his theory of relativity, time and space have never been the same. Time was considered an absolute and unchanging magnitude until then, and it was demonstrated to be relative. Time and space are interconnected and inseparable, much like the speed of light, which is always constant regardless of the source or motion of the observer. Einstein proposed a moldable spacetime geometry as a solution to explain the constancy of the speed of light in all inertial reference frames. In the early 20th century, it seemed incredible to many that time and space are not absolute. Gravity. The universe consists of 3 spatial dimensions and 1 temporal dimension. To locate any object, we must not only place it in its spatial position, but also in time. This continuous spacetime can be represented as a network and is affected by velocity and mass. Mass and velocity slow down the passage of time relative to another observer. Our view of the universe depends on the observer, their mass, and velocities. Someone traveling at 90% of the speed of light experiences time passing more slowly compared to someone traveling at 1%. Even though they perceive it essentially the same. An object with mass causes a curvature of spacetime, which we call gravity. Thus, an observer subject to Earth's gravitational field will age more slowly than one situated in the vacuum of space. Curvature in spacetime affects time, so time is never the same for everyone. None of us escape relativity, although relativistic effects are more noticeable in the presence of large masses and velocities. The truth is that each of us is subject to different masses and velocities, which is why we carry our time with us. The differences between people on our planet are minimal, on the order of a trillionth of a second. We are subjected to the same gravitational field, our masses, and the velocities at which we move are negligible to the cosmos, and we do not notice any temporal discrepancy. That is why we have always believed that time is absolute, but nothing in the universe is as it seems. When there are high velocities, several kilometers per second or reaching 10% of the speed of light, relativistic effects become more significant. This means that the perception of time and space is significantly altered, as predicted by Albert Einstein's theory of relativity. Planets and stars in these extreme scenarios act as temporal dilators. A paradigmatic example of this phenomenon is black holes. These objects have an enormous mass concentrated in a very small space, causing gravity so intense that even light cannot escape. At the singularity at the center of a black hole, space-time curvature reaches its maximum, and time seems to stand still from our perspective. Black holes can be understood as extreme deformations in the structure of space-time, where the laws of classical relativity are no longer applicable. This is precisely the meeting point between general relativity and quantum mechanics, where the two fundamental theories of physics encounter their limits, raising questions about the very nature of the universe. Time dilation and contraction, effects predicted by the theory of relativity, have been experimentally confirmed on numerous occasions. A practical example of this is the relativistic correction that atomic clocks aboard GPS satellites must make. Without this correction, our GPS applications and navigation systems would show significant deviations of tens of meters, seriously affecting their accuracy. Furthermore, the ability of spacetime to be molded by the presence of significant masses is evident in astronomical phenomena such as gravitational lenses. In these cases, light emitted by distant objects is distorted when passing close to massive masses on its way to Earth, resulting in duplicated or even quadruplicated astronomical images. In summary, understanding relativistic effects in the presence of high speeds and massive objects is fundamental both for theoretical physics and practical applications, offering us a fascinating insight into the flexible and malleable nature of spacetime in the universe. The LIGO experiment, which detected gravitational waves, represents another significant milestone in confirming Einstein's general theory of relativity. These waves are vibrations in the very fabric of spacetime, and their detection provides concrete evidence that spacetime can expand and contract, thus revealing a fundamental characteristic of the universe's structure that was previously only theorized. In this sense, the universe can be conceived as a vast cosmic ocean, where space-time behaves like a medium that can be distorted and folded under the influence of matter and energy. This analogy helps us visualize how significant masses, such as stars and black holes, can curve space-time around them, generating observable gravitational effects like light deflection or the stretching and compression of time. When we unify space and time into a four-dimensional entity, we obtain Minkowski spacetime, a conceptual structure developed by the German mathematician Hermann Minkowski, who was Albert Einstein's professor. Minkowski was instrumental in formulating the geometry of spacetime, which is crucial for the modern understanding of relativity. In 1908, Minkowski expressed the idea that space and time, considered separately, were destined to fade into shadows, and only their union in spacetime could represent true reality. This vision was a crucial inspiration for Einstein and contributed significantly to his development of the theory of relativity. In 1929, the discovery of the universe's expansion, observed in the redshift of distant galaxies, led to an even deeper understanding of the relationship between spacetime and cosmic expansion. Relativity predicted that it wasn't the galaxies moving away from each other, but rather the spacetime containing them that was expanding. This phenomenon is attributed to a form of energy intrinsic to spacetime itself, called dark energy, whose exact nature remains a fascinating enigma in modern cosmology. The influence of dark energy becomes more apparent as the distance between galaxies increases, explaining the observed relationship between the recession velocity of galaxies and their distance, a phenomenon known as Hubble's law. This groundbreaking discovery has reshaped our understanding of the cosmos and continues to inspire profound research into the nature of spacetime and its role in the universe's evolution. The phenomenon of the universe's expansion is fascinating and raises profound questions about the very nature of spacetime. As you mentioned, this expansion is not uniform on all cosmic scales. While on very large scales, such as between distant galaxies, expansion is evident and dominant, on smaller scales, such as within a galaxy cluster, gravitational force can be strong enough to counteract it. This is the case with the Milky Way and Andromeda, which are mutually attracting each other due to gravity. One of the most surprising implications of the universe's expansion is that it affects not only space, but also time. This idea may seem bewildering at first, but it is a direct consequence of considering space and time as interconnected components of spacetime. The notion that the universe's expansion affects time is something that few physicists initially considered, even after the discovery of accelerated expansion in 1998. However, if we think of gravity as a curvature in the fabric of spacetime, it makes sense that a change in the universe's expansion would also have an effect on the temporal dimension. This concept challenges our everyday intuition, where we tend to think of time as a universal constant. However, Einstein's general relativity teaches us that time is relative and can be affected by the geometry of spacetime. Thus, the rate of the universe's expansion can influence the perception of time in different regions of the cosmos. This idea opens new perspectives in understanding how the universe evolves over cosmic time and raises intriguing questions about the relationship between the expansion of spacetime and the dynamics of astrophysical phenomena. Exploring these ideas allows us to deepen our understanding of the universe as a whole and the fundamental interactions governing it. What follows is nothing more than a hypothesis, but it has a certain logic. Space expands and so does time. In a way, it can be said that time passes more slowly as the universe's space expands. We know that, as general relativity states, time passes more slowly in an intense gravitational field than in a less intense one. So, as the universe expands, cosmological objects such as galaxies move away from each other more rapidly. Lorentz transformations, which are part of Einstein's special theory of relativity, indeed lead us to surprising conclusions about the nature of time when approaching speeds close to the speed of light. One of these conclusions is time dilation, where time appears to pass more slowly for a moving observer compared to a stationary one. This phenomenon has been experimentally confirmed numerous times, even with subatomic particles accelerated to significant speeds in particle accelerators. If we extrapolate this idea to the universe as a whole, the fascinating notion emerges that time may have passed at different rates at different moments in cosmic history. According to this perspective, the universe's expansion could be partly a consequence of time passing more rapidly in the distant past. This hypothesis poses interesting challenges for our understanding of the history and evolution of the cosmos. For example, the discovery of galaxies that seem to be highly evolved barely 180 million years after the universe's birth could be explained by temporal dilation. If time passed faster in the past, then the universe would be much older than our current estimates indicate. However, as observers immersed in our own temporal framework, our perception of time remains constant. For us, time seems to pass uniformly, and we do not perceive the effects of temporal dilation on a cosmic scale. The question of whether the passage of time reflects the measure of the universe's expansion is a deeply intriguing one in cosmology. If time is a manifestation of the universe's expansion, this would suggest a fundamental connection between temporal dynamics and the evolution of the cosmos as a whole. Regarding the detection of the universe's expansion as accelerated, this phenomenon is based on astronomical observations showing that distant galaxies are receding from us at ever-increasing speeds. This is evidenced by the redshift observed in the spectrum of light emitted by these galaxies, indicating their recession. The acceleration of this expansion is deduced from the observation of distant supernovas and other cosmological measurements. This discovery played a crucial role in the development of the theory of dark energy, which is postulated to be responsible for driving this cosmic acceleration, although its exact nature remains an enigma in current cosmology. Your reflection raises an interesting perspective on the nature of the universe's expansion and its relation to time. The idea that the accelerated expansion of the universe could be interpreted as an illusion caused by time is intriguing and leads us to consider the complexity of space-time geometry. Imagine visualizing the universe not only in terms of three spatial dimensions, but also with a temporal direction perpendicular to those dimensions. In this approach, the acceleration of the universe's expansion would be perceived as a manifestation in this additional temporal direction, suggesting that the expansion of the universe could be more a consequence of temporal dynamics than an intrinsic property of space. This concept can be illustrated with the example of a spaceship approaching the speed of light. From our perspective, we would observe that time inside the ship slows down, while for the occupant of the ship, our time would seem to pass faster. This asymmetry in the perception of time is a direct consequence of Lorentz transformations in the theory of special relativity. Applying this idea to the expanding universe, we can imagine that different observers in distant regions of the cosmos may experience time differently due to their relative velocities and local gravitational fields. Calculating time for a hypothetical inhabitant of Andromeda, as you point out, would be a monumental challenge due to the complexity of gravitational effects and the variation of velocities at play. This idea leads us to question the very nature of time and how we perceive its flow in a constantly changing universe. Understanding the relationship between time and the expansion of the universe is fundamental to our vision of the cosmos and raises profound questions about the essence of reality and perception. Exploring these ideas takes us to the very frontier of our understanding of physics and cosmology. Your reflection on space-time and its relationship with the flow of time according to relativity leads us to consider the profound interconnection between the geometry of the cosmos and our perception of time. It is true that, according to the theory of relativity, velocities and gravitational fields significantly affect the perception of time. This implies that, in a fundamental sense, all objects we observe in the universe are seen in the past due to the limits imposed by the speed of light and the effects of temporal displacement. The notion that now is relative, and that what we see is a kind of temporal illusion, is an idea that challenges our common intuition about time. In regions of the universe with high gravity or high relative velocities, time may pass differently compared to our own experience. This raises the fascinating question of whether there is something beyond space-time as we know it. The idea of additional dimensions beyond space-time, as you suggest, is an idea that has been explored in theoretical physics, especially in the framework of string theories and quantum gravity. In these theories, The existence of a hyperdimensional space underlying three-dimensional spacetime and time is postulated, a space where fundamental forces and elementary particles manifest. There are several lines of evidence suggesting the existence of these additional dimensions, such as the progressive redshift of distant galaxies due to the expansion of space. This phenomenon, as you mentioned, sets a limit on our visible universe, beyond which galaxies are so distant that spacetime is carrying them away at speeds greater than light, preventing their light from reaching us. This concept leads us to a deeper understanding of the nature of the cosmos and challenges us to consider new perspectives on reality beyond our everyday experience. Exploring these ideas takes us to the limit of our current understanding of physics and invites us to imagine the mysteries of the universe that are still to be uncovered. At the forefront of this exploration lies the intriguing phenomenon of the expansion of the universe. This expansion, occurring at a speed exceeding that of light, defies our conventional notions of cosmic reality. As we delve into the implications of this cosmic expansion, we are confronted with profound questions that push the boundaries of our understanding. Consider, for instance, the light emanating from distant galaxies situated more than 40 billion light-years away. According to our current measurements, the age of the universe itself falls significantly short of this vast distance. This apparent paradox raises a fascinating enigma. How is it possible that the light from these distant galaxies has traversed such immense distances over a period much longer than the age of the universe as we currently comprehend it? Delving deeper into this puzzle leads us to grapple with complex concepts such as the cosmological horizon and the true nature of spacetime. The cosmological horizon represents the boundary beyond which we cannot observe or interact with the universe due to the finite speed of light and the expansion of space itself. It serves as a tantalizing frontier, teasing us with the mysteries that lie beyond our reach. Furthermore, our exploration of the true nature of spacetime unveils a rich tapestry of interconnected dimensions, woven together by the fabric of the cosmos. Einstein's theory of general relativity provides a framework for understanding the dynamic interplay between matter, energy, and the curvature of spacetime, offering profound insights into the fundamental structure of the universe. As we contemplate these profound questions and grapple with the complexities of cosmic reality, we are challenged to expand our conceptual horizons and embrace the profound mysteries that await our discovery. In doing so, we embark on a journey of intellectual and philosophical exploration that transcends the limitations of our everyday experience, inviting us to glimpse the boundless wonders of the cosmos. The hypothesis that the quantum vacuum plays a crucial role in the expansion of the universe adds an additional layer of fascination to this enigma. Despite its name, the quantum vacuum is far from an absolute void. It is actually teeming with activity. Quantum fluctuations and virtual particles constantly emerge and disappear in this environment, generating an intricate dance of energy. This dynamic behavior stems from the inherent uncertainty of quantum mechanics, where particles briefly borrow energy from the vacuum before returning it. These fluctuations may seem ephemeral, but their cumulative effects can be profound. It is suggested that these fluctuations may give rise to negative pressure acting as a driver, propelling the expansion of space itself. This intriguing concept parallels the behavior of dark energy, a mysterious force thought to be responsible for the accelerated expansion of the universe. By delving into the quantum realm, scientists hope to gain deeper insights into the underlying mechanisms driving cosmic expansion. Furthermore, the analogy of a vacuum tube inflating due to pressure difference provides a helpful visualization, albeit at a vastly different scale. In this analogy, the pressure arises not from conventional physical forces, but from the dynamic interplay of quantum fluctuations. This perspective underscores the interconnectedness of seemingly disparate phenomena, bridging the gap between the microscopic world of quantum mechanics and the macroscopic scale of cosmic expansion. In addition to the enigmatic role of the quantum vacuum, quantum entanglement emerges as another extraordinary phenomenon that challenges traditional notions of space and time. When two entangled particles are separated by astronomical distances, they exhibit a peculiar correlation that defies classical intuition. Remarkably, changes to one particle instantaneously affect its entangled partner, regardless of the vast spatial separation between them. This seemingly instantaneous transmission of information between entangled particles has puzzled scientists for decades. It appears to violate the speed of light restriction imposed by relativity, suggesting the existence of underlying principles beyond our current understanding. While quantum entanglement has been demonstrated experimentally and plays a crucial role in emerging technologies such as quantum computing and cryptography, its fundamental nature continues to elude complete comprehension. The mystery of quantum entanglement remains a focal point of research in the field of quantum physics, inspiring new theoretical frameworks and experimental investigations. As scientists strive to unravel the intricacies of entanglement, they venture into uncharted territory where the boundaries between space, time, and information blur. The quest to understand this profound phenomenon offers tantalizing glimpses into the deeper fabric of reality, challenging us to rethink our fundamental assumptions about the nature of the universe. The suggestion that there might exist a means of communication beyond space-time that allows for quantum entanglement is a truly provocative idea. This notion raises fundamental questions about the very nature of the universe and how its most basic components interact. Delving into these concepts takes us to the cutting edge of theoretical physics, challenging us to reconsider our perceptions of reality at its deepest level. Quantum entanglement, often described as spooky action at a distance by Einstein, Podolsky, and Rosen in their famous EPR paradox, has long been a source of fascination and intrigue within the scientific community. The phenomenon defies classical intuitions about locality and causality, suggesting the existence of hidden connections that transcend conventional notions of space and time. Moreover, the exploration of quantum entanglement leads us to contemplate the possibility of additional dimensions beyond the three spatial dimensions and the temporal dimension that we know. In theoretical physics, frameworks such as string theory and brane theory propose the existence of extra dimensions beyond our familiar three-dimensional space and one-dimensional time. These extra dimensions, if they indeed exist, could provide a rich tapestry upon which the intricate dance of quantum entanglement unfolds. Some theories suggest that these extra dimensions could be compactified or curled up at scales beyond our current observational capabilities, effectively hidden from direct detection. However, their influence on fundamental interactions, including quantum entanglement, could be profound. These additional dimensions offer a tantalizing avenue for understanding the underlying mechanisms that govern entanglement and its potential for communication beyond spacetime. Furthermore, the quest to comprehend the nature of communication beyond spacetime intersects with broader philosophical inquiries into the nature of reality and consciousness. Concepts such as non-locality and the interconnectedness of all things challenge traditional Cartesian dualism and suggest a more holistic understanding of the universe, where boundaries between observer and observed blur. This exploration of communication beyond spacetime is not merely an academic pursuit, but also holds profound implications for technology and our understanding of the cosmos. The potential for harnessing quantum entanglement for secure communication, quantum computing, and teleportation has inspired intensive research and development efforts worldwide. In summary, the investigation into the possibility of communication beyond spacetime through phenomena like quantum entanglement opens up a vast landscape of inquiry at the intersection of physics, philosophy, and metaphysics. It challenges us to transcend the limitations of our current understanding and explore the mysteries that lie beyond the horizon of conventional thought. The issue of information loss in black holes is undoubtedly one of the most fascinating and persistent puzzles in modern physics. According to the laws of physics as we know them, information is never destroyed, but rather conserved. This principle of information conservation is a cornerstone of our understanding of the universe, asserting that nothing is created or destroyed, but simply transformed. However, black holes intriguingly challenge this idea. These mysterious cosmic objects, resulting from the gravitational collapse of massive stars at the end of their lives, represent true natural laboratories where the most extreme forces of gravity and relativity are spectacularly manifested. According to Einstein's classical theory of general relativity, when matter collapses into a black hole, all information associated with it appears to be irreversibly lost behind the event horizon, that boundary beyond which nothing, not even light, can escape. This apparent contradiction between information conservation and the physical processes that occur within a black hole has baffled physicists for decades. Numerous theories and conjectures have been proposed to address this dilemma, from the hypothesis that information may be stored in some form on the surface of the event horizon to speculation about the need to modify the laws of physics as we currently understand them. The study of this enigma not only challenges our fundamental concepts of information and gravity, but also provides a unique window to explore the limits of our understanding of the universe. This puzzle has sparked intense research in the field of theoretical physics, leading to various theories and speculations to resolve it, such as the well-known paradox of information in black holes. One of the most intriguing proposals is that the supposedly lost information in a black hole could be somehow preserved elsewhere in the universe, outside conventional spacetime, as you suggest. An exciting hypothesis is that this information could eventually return to the quantum vacuum, where the fluctuations and virtual particles that constitute the fabric of the cosmos originate. This concept of information conservation in the context of black holes has led to the exploration of a variety of ideas, from the possibility that information escapes in the form of Hawking radiation to speculation about additional dimensions or parallel universes where information could be preserved. These are just some of the fascinating paths that research in cosmology and theoretical physics is taking to unravel the mysteries of black holes and their relationship with the fundamental laws of the universe. The relativity of time in the cosmos is an extremely intriguing topic that invites us to reflect on the nature of time itself and its perception in the vast stage of the universe. Your observation about the impossibility of knowing the speed of the individual clocks of the numerous celestial objects is very accurate. Although the cosmos is filled with stars, planets, and galaxies, the information we receive from them through the light that reaches us provides only a snapshot of their state in the past. It reveals nothing about how time elapses in the present for them. This relativity of time implies that events and changes in astronomical objects occur on timescales that can be radically different from ours. In fact, some processes may be so slow that it would be impossible to observe their evolution in real time from our human perspective. For example, the birth and death of stars, as well as the formation and evolution of galaxies, are processes that occur on timescales that can span millions or even billions of years. This concept becomes even more profound when we consider that for beings on a distant planet, their entire history could unfold in a relatively short span of time in relation to us. This forces us to contemplate relativity not only in terms of space, as Einstein did, but also in terms of time. It shows us the importance of taking into account the cosmic timescale when studying the universe and its phenomena, as well as the need to develop new tools and methods to adequately understand the processes that shape the cosmos over timescales immeasurable to us. We remain lost in this small world, wondering about the nature of the cosmos, watching how we expand. Galaxies are getting farther away from us. We are increasingly alone in an immense cosmos that seems to expand before our eyes, but indeed it does. If you enjoyed this video, give it a like and subscribe. Contribute on Patreon to keep the channel active, share on social networks, and leave your comment. A cosmic hug to all. Ki.